Hey, John here. Before we start this video, I really want to thank my patrons. You've been really generous, really helpful in supporting this channel. I really appreciate everything you've done. Now, before we talk about CPM, let's talk at least about this machine right here. It's one of the machines that is of the class of machine that CPM was designed to run on, all right? So the way this thing would have been purchased is in a kit form. And it would have come with a manual. Here's a manual right here for this. This is actually the manual for that real machine. The serial number matches and everything. This would have, does have all the instructions in it on how to solder in all the chips on all the boards and how to configure the power supply and everything else. And, it even has like detailed drawings of which screws go with which nuts and stuff, to the point where, I'm actually surprised that anybody that would try this would need that much information on how to assemble it. But my point is, this is a very thorough manual, all right? Now, let's run this for a second before we take it apart. Let's go ahead and plug it in. This works. And so what this thing has here, what I'm looking at, is a sample program that they give you, and they say after you're done assembling it, try running this program to give it a general check it out, right? So you plug it in, you turn this thing on. I forgot how loud it is. You know what? If I take the cover off, I think it makes a lot less noise. So let me do that. We'll look inside in a minute. That's why I had the bolts out. So let's run this program. What it's going to do is it's going to input a byte on port number FF. And then it's going to just output it back out to port FF and branch back to 0. And on this machine, what that means is port FF is one way to read the current value on all these switches right here, okay? And port FF, when you write to it, will put a value on these 8 LEDs. The 8 bits of the accumulator will be outputted on here, okay? So what it will say is hit this button here, it stops the system and reset the system. When you reset it, it's supposed to light up every light on the panel here, which it does, okay? These are different over there, but all these lights should go on. So that tests that situation. And of course, it's stopped. The wait, where's the wait? Wait, there it is. This LED is on, telling us that the CPU wants to run, but it's being held hostage. It's stopped because the front panel hasn't halted, okay? So when it's in this mode, I can input in a program, and they give you the instructions and the binary values in here. So what you need to do is start entering it at address 0. So all the switches down are address 0. Now, when we're entering in data, you use these switches here are the data switches to input data into the memory. So I'm at address 0, and I want to put in a DB, which is a 11011011. Okay, that's the opcode for the input operation. And I can say deposit. You click the switch up here like that, and you can see these LEDs now match these switches, and this address here is 0. So that means I just put that into that location. The next byte should be FF, so that's all ones, and I can click this switch that says deposit next, which advances the address. You can now see it's 1, and you can see the data there now is all FF. Then I go to D3, which is this. Deposit that one in the next location there. Then I want to do another FF. These FFs are the port addresses, by the way, for the input and the output command. So I just entered in 2 instructions. Each one of them has 2 bytes. Then I'm going to enter an instruction that says jump back to address 0. So that's going to be a C3, which looks like this in binary. And I'm going to deposit that. That's the opcode for jump, unconditional. And then I want to jump to address 0. So that means put a 0 in there and another 0. And I'll just put a bunch of extra zeros in there just to clear out the memory for no good reason. If you then go back with the switch, I can say examine the data that's at the location in this address here, which is all zeros right now. And there's my original value. That's the DB, right? 11011011. And I can say examine next. And I can toggle through this program and make sure I didn't make any mistakes. Now, this is a little bit tedious. On the retro board, now you know why I hooked up a Raspberry Pi to toggle in all these bytes, all using a parallel chip, excuse me, a parallel port chip. Okay, when we're done with all this, you can then, of course, reset it again, and you can hit run. And now the CPU is running, and while it's running, the front panel shows you all the address and data values while this CPU is fetching instructions and doing stuff. I'm a little bothered by the fact that all these lights over here are lit up. I don't know why. It should be interacting with any address locations that would require these to be on, but that could just be noise between instructions. To see if it works, we can play around with these switches. So it's obviously working in spite of the fact that we see a little noise on the address bus over here. And like I said, what this program does is it reads the value on this 8-bit port that these switches are on, and then it writes that value back out to here. So this thing works, all right? So much for demonstrating the machine and how to use it from the front panel, okay? Go ahead and unplug it. If you actually use one of these or have one, be careful with the power, because as we'll see in a minute, I'm going to let the capacitors discharge for a few seconds. They're gigantic. And the 110 volt AC line is like right here. So you're inclined to grab it like this. And you ain't going to be too comfortable if you do that. All right. So power's off. I can see the cord here. Let's chip this thing up and look and see what's inside. Okay, so this is what's inside this thing. Hardly any slots are filled right now. We'll talk about those in a second. This card right here is the CPU. I don't need to take it out. There's a card here that is the front panel full of LEDs and stuff, and with the switches and all that, right? This card right here is some memory, and I can just grabbing it, only having it on that long, this is already warm enough where while I could, in a bar bet, keep my hand on it, it's already too hot to want to keep my hand on it. And there's 4 7805s on here. And remember that these can are rated up to a ½ amp. So this might be, 2 amps total of power to run all these chips on here. So that's what, 10 watts just for this board. And this board is, I think this is a 32K bytes of RAM. Now I put this board in here simply because it was handy and I needed some memory for this machine. Right now it has no memory in it, okay? We'll come back to the memory in a second. This is a power supply. It's something linear. Look at the size of this transformer. Now if you had a MITS Altair 8800, which is basically the same machine, but it's an earlier design. One of the things it's known for is that its power supply is not as powerful as you might always want it to be. So one of the things that happened when IMSAI came out with the 8080 a year later is they put this gigantic power supply in there, so nobody could ever complain that they had an anemic power supply. Massive capacitors for the 5-volt side, and another pair of capacitors over here for the 12-volt side. Look at all these slots. There's 22 total slots in here. One of them is the front panel, one of them is the CPU. That leaves you with 20 leftover slots. You might think, what are you going to do with all that? Well, this is what you're going to do with it. This is a MITS 4K RAM board, all right? And this is not even their first one. Their first ones had 1K on a board, right? Now remember, these machines can address up to 64K of RAM, and 4K was the size of that era. So if you wanted 64K, you needed to have 16 of these in there, okay? It wasn't until a year or two later when they were able to make these bigger boards, okay? Which then alleviated the need for the extra 16 slots, right? But if you had the 4K board, you would have 16 of these in here, plus 2 of those, and that would leave you with 4 empty slots. Now, realize as it is, there's no I/O. One of those slots would have been a serial port, one of them would have been a disk controller, one of them might have been like an EEPROM board, so when you turn it on, you don't have to toggle in your bootstrap code. And then you'd have only 1 slot left, maybe, a parallel board for a printer or something. And that's kind of the way it worked back then. Okay, so, takeaway, RAM came in expensive increments of either 1K or 4K boards. Mostly 4K by the time you up the ante enough to want to buy CPM and stuff like that. And this was the kind of machines you would have used. You would have only bought as much memory as you would need, because these boards, even in mid-70s money, was either $200 or $300 a piece. So, what else here? These are ribbon cables that connect to DB25s that are mounted to the back panel here. These things with these edge connectors would have come up and plugged into boards in here. These would have been, your serial board. So that's how you would have hooked up your DB25s. Your floppy disk controller would have also gone out the back there as well.
All right, so I don't have the CPM manuals that came with any software for the 8080 that I have. I just got the 8080. I do, though, have the original manuals for an Altos ACS 8000 that came with CPM. So here's the original disc. This is what you would have gotten if you bought CPM, like from Digital Research, DRI, the company that originally wrote and sold it. Now, normally you wouldn't buy it directly from them. You'd get it with a kit that you bought, or it would be distributed by a vendor like Altos or IMSAI or somebody like that. Now, even if you bought a turnkey system like an Altos, it comes with everything you're going to see right here, and this is what we're going to use to port CPM to the Retro board. This is just the Altos branded copy of the regular CPM, and this is going to be delivered on a single density 8-inch floppy disk like this. And it has, on an 8-inch floppy disk, has 77 tracks. The head moves in and out this way. There's a hole here, and you can see a little dot inside there. I guess it might appear better if I put it over the white manual, I guess. And that is an index hole. When the disk spins around, each time it goes around once, this is what we call a soft sector disk, which means there's a little hole on the little brown disk inside this black envelope that when it spins around, there's a little light in the floppy disk drive that sees the hole go by to let it know that it's at the beginning of a track. At that point, the sectors are written around around the circumference of the disk inside. This notch here is a write protect notch. On an 8-inch floppy disk, having it open like this means it's write protected. You can put a piece of tape on here and cover this up, and then it becomes a writable disk. Now, this particular floppy has 77 tracks, like I just said, and it has 26 sectors around like this. So each track would have the same number of sectors. If you drew them on like with a Sharpie, it would look like pie slices all coming out concentrically. Now, some floppy disks are double-sided. You can get a drive that's got a head on both sides, in which case you've got a front and a back side track. The two tracks combined would be called a cylinder. In terms of, like hard drives are very often have many heads, and all heads on the same track would represent one cylinder, from the distance out from the center of the drive. Okay. Now, CPM is designed to work on this kind of media with this format, right? 77 tracks, 26 sectors. And if you bought it, you get your license that comes with it, and you get these 7 booklets with it. All right, so let's make sure that we see these, know what they are. Go ahead and download your own copy of them if you want. Some of these we don't need really for the retro project, but if you're really new to CPM, you might want to thumb through all these, because this is your introduction to CPM features and facilities. If you have ever used DOS before, you'd know it was basically stolen from CPM. And of course, endless debate. Did they really steal it? Did they not? Who really stole it, right? Microsoft actually bought their code from another company that probably stole it. So Microsoft didn't really steal it. I don't know. You'll recognize most of these commands. You type dir to list the files on, the directory listing of your files, and you type in the word type to list it on the console, and you type ERA to delete a file, and REM to rename a file, and stuff like that. Okay, so this will talk about the high level names, and this is where your TTY colon, your console colon, like LST colon, and things like that. These are all CPM things. This is what they name the various devices, the printer, the PRN, and the LPT1, and all this other stuff. Here's our PTR, they call that printer. And, well, actually, that's the paper tape reader. Oh, excuse me. I'm so embarrassed. I shouldn't have said. Anyway, so LST is the list device for this one, okay? Anyway, this will go through and define a lot of that sort of stuff and how to use the basic commands that you would normally need to use if you live in the world of CPM. Then there's a user's guide, which you might ask, what was the thing I just saw? Well, this is actually this particular user's guide is a list of the features in CPM2 that are different if you already are familiar with 1.4. So that's kind of like your release notes. The interface guide, if you're a Unix programmer, you know what's in section 2 of the online manual. That's what this is for CPM. Section 2 holds all the doc for all that what we call system calls. These are the services that the CPM operating system provides, and it tells you how to call them as subroutines. If you want to ask, hey, what's the current disk that's been logged in? If you want to rename a file, the login vector is actually a really interesting name for all of the a list of all the drives that exist in the system. Is there a drive A? Is there a drive B? And so on. Writing into a file, reading, and stuff like that. So these are your system calls. And there's an extra sheet of paper in this particular manual shoved in here. So this is CPM 2, but for CPM 2.2, to upgrade the manual, I guess they didn't want to have to reprint them all. They just shove in a piece of paper and say, oh, by the way, there's 2 extra system calls in here and how to call them. So if we scan this, get an online scan of this, it might be missing this extra page. So we'll look at that when the time comes. This is the manual you're going to know and love if you want to tinker around with CPM and make it work on a new piece of hardware like a retro board, okay? This manual here, if we open it up and look for the middle of this manual, from the middle, exactly from the middle to the end is all source code of a sample BIOS. And it also, the first 2 or 3 pages is the cold start loader. This is the bootloader. This would go into the flash ROM, flash chip on the retro board. Okay, so there's the boot ROM image, and then down here is the BIOS that you need to assemble and then combined with the operating system stuff. We'll look very closely at this when we do our when we want to boot up CPM, okay? And what else do we got in here? There's the DDT manual. This is your interactive debugger. Everything's command line in CPM, so it's command line interactive debugger. So you run a program and it'll tell you, here's the instructions that executed in this order, and you can say, hey, show me what the current value of the registers are while the program runs. You can dump out memory and make sure that the thing is working correctly as you would expect, okay? That's what DDT is. Now we have a thing called ED, which is the line editor that comes with CPM. I used this for many years until I found a version of Wordstar that I could use to accomplish the same thing. And we can go ahead and find executable binaries of Wordstar that'll work with the terminal emulators on the Raspberry Pi or Linux or something, or even Windows or something like that, okay? Which is easier to use. Wordstar, you heard of it. Sometimes writers will actually comment that they think Wordstar is like the greatest editor they've ever used. And we'll have a look-see at it. What's this thing on here? So the dark brown one, you might not be able to read it. This is the manual for the assembler that comes with CPM. Okay? Now remember, CPM was written to run on an 8080. Yeah, so this assembler is an 8080 assembler, and the instruction mnemonics will be the Intel style instructions. Okay, well, take a quick look at this at some point, because you're going to need to be aware of this, because we'll discuss this when we look at the sample BIOS code, and a lot of the documentation for how to deal with the BIOS is all written in 8080 assembler, because obviously we got a Z80. I've been talking about Z80 assembler the whole time. You'll be able to see some of the differences. They're minor in my opinion. Luckily the Z80 assembler is more clear at what's going on. The 8080 is not so much. As an example, when you want to push the BC register pair, you push B. You don't push BC, okay? You just say push B, because everybody knows that that means push the register pair. Then you store A, the accumulator stacks, STAX is like store A extended or something like that. And that means store the accumulator into memory at the 16-bit address in the DE register pair. And the way you write that in 8080 is stacks D. And LDAX B is load A from memory at the address in the BC register pair. So these two, some of these, instructions are not exactly as robustly easy to understand or recognize than in contrast to the Z80 ones, where you want to push the BC register pair, you push BC, right? So anyway, I'll show you where you get these. We download them online, get your own copy, because you're going to want these if you want to follow along. So I put some links into the repo here for the CPM's code for the Z80 Retro project here, all right? So I made a couple of changes in here. What I did is I moved the SD card instructions into its own README file because it's starting to get too big. So time to refactor, right? Here's a link back to the retro board schematics and all that. This is the SD card right there. Here's the hello program that we talked about before. And here we have the where to download CPM. You don't actually have to do this, because what happens is, as I say down here, see the CPM22 directory for details on how to download all this stuff and prepare them for assembly. Let's take a quick look in here. What I got in here is a make file and nothing else. So what happens is, if you type make in this directory, what it's going to do is it's going to go out to this website over here, which is in Germany, and grab the source code for CPM2. Okay? And then it's going to unzip the file and grab out the source code for the CPM 2.2 operating system and leave it in this directory here. Now, I don't put this in my site because it turns out that CPM is very widely distributed, and there are like an official bundle of files that were put out a few years ago. Even like the Computer History Museum has officially made them available and stuff like that. But technically, they're still under copyright, and I don't personally have a letter from the company that owns the rights to host them, so I'm not going to. This one here allegedly does have an official permission to host this and distribute it to whoever wants it, okay? And they've got manuals and everything else over there. So what this is going to do is it's going to download and grab the file that you want, okay? From where it is. All right, so that's one thing. Otherwise, you can do it manually by clicking on these links and surfing through the website yourself. It's kind of a neat place to browse around and look and see what they've got in there, because one of the things they have is a bunch of manuals. So here's where you can grab your own copy of the booklets, or this link down here, which is like one big book that has all of them in one big wad. This one down here is probably a better shot, because if I looked and it looked like this one was published in 1982, and all these other ones were before that. So if there's any errors in these, and they are corrected, they're probably corrected in the big wad down here. But like I say, if you're a purist, you want to get these pamphlets up here. Maybe all of the above while you're at it, okay? What else we got in here? See the retro directory for details on how to assemble and install CPM on an SD card. So this is what we want to do. This is the main goal of just getting a sign of life out of all these pieces here, all right? So let's start by looking at what's inside the hello, welcome to the world of CPM manual here, the introduction to features and facilities manual. Now, the reason we want to look at this one here is because it introduces you to basically DOS, all right? So if you read through here, you'll recognize that dir and rename a file and type a file to see it on the screen. We're familiar with these if we've ever used DOS. More importantly, it tells you about, these other commands on how to use the assembler, the editor, and how to dump out a file. And they don't have DDT in here, but DDT has its own manual. So I guess you don't really need it in here. But so does ed, and yet that's in here. Well, whatever. These are just example commands anyway. The reason I want to look at this right now is if we scroll down to right here, it says, look, CPM is designed to run on an 8080 or the Z80 processor. Gives you a little high-level discussion about what's what and what they're thinking about. And there's some numbers in here that suggest that this is actually the manual for CPM version 1.4 and not 2.2. And the reason for that difference, or reason for me noticing the difference, I should say, is because it talks about, like, it can have up to 4 disks, but CPM 2.2 can have 16 disks, and CPM 1.4 could only have 64 files on a given disk, and CPM 2.2 can have hundreds. Okay, so other than that, this is still perfectly reasonable. It's a really high level description, and we have more available to us than we did in version 1.4. These things are the important part. It says, look, CPM is logically divided into these distinct parts: TPA, CCP, BDOS, BIOS. We write this. This is just the drivers, and we've already written them all. Every one of the things that we need for the BIOS, I'm exaggerating a little bit, not everyone, but certainly every driver we need that goes into the BIOS, we've already written and tested and verified is done. So we kind of got all the Lego blocks. It's just a matter of putting them together. Almost. The other thing that we need to do in the BIOS is to deal with, we have to tell CPM all about our disk drives, okay? We know how to operate them, but we need to teach CPM how they, how many blocks, how many sectors there are, and where everything is, so that it knows not to try to write more data onto the disk than the disk can hold, that sort of stuff. And then there's some other malarkey going on, some of which we can ignore, other things we kind of have to make our SD card act as if it's a great big floppy disk, because CPM really wants to see the world as, some floppy disks, all right? And that's the part that we have not yet done. But everything else is ours on a silver platter already. I would argue the hard part's done. The only hard thing left is understanding how to glue this stuff together, okay? Now, fortunately for us, the TPA, the CCP, and the BDOS, this is already taken care of for us by the CPM system itself. Okay? And you can read again, relive how DOS works, right? DOS was an upgrade, you could say, from CPM, but basically it's the same thing if you use early versions of DOS. And down here it says, the operating system is fully featured. You can search for files, open them, close them, rename them, read data out of a file, write data into a file, and you can select which disk you want to, transfer data from, into, and so on. All right, so this is the main thing that you get from this BDOS over here. Right, which is why they focus on a disk operating system here. Now, it also includes stuff that print things on the console and the printer and all that, but that is trivial in contrast to dealing with the disk, okay? So, you can read the rest of this to figure out, terminology and relive early DOS years and pre-DOS years, I should say. Now, you've got the features and facilities here. If you use 1.4 and you're upgrading to 1.2, you can read this. It summarizes the differences. You got the text editor, DDT. These are applications that we can play around with later once we can actually boot and run the OS so that we can load and run these programs, all right? The interface guide is worth a quick look right now. This thing is going to tell you when you run a regular application program, how do you invoke the operating system? And it gives you this nice picture right here, okay? This tells you that the bottom part of memory is used by the operating system for its parameters and stuff. Then there's this hole right here called the TPA, Transient Program Area. This is where programs go when you load them off the disk to run them. By definition, those are transient. The program will start running, you do what you're going to do, and when you're done, you exit the program and you go back to the operating system. Then you might load a different program, and they would replace the first one, run it in here one at a time. That's what we used to do here, okay? Now, the size of the TPA is dependent on how much memory you can afford to buy. We're playing around with CPM 2.2, and that system is such that the smallest amount of memory that your entire system can have is 20K. So if you have 20K, the CCP, the BDOS, and the BIOS, these three pieces here sit all the way up at the top of the memory you do have, so the high memory will end at 20K. If you have more, then this moves up further and further, okay? To make the TPA bigger, so you can have more data or you can run bigger programs. Now, what is the CCP? The CCP stands for Console Command Processor, and that is the thing, if you're a Unix person or a Mac person, that's your shell, okay? The Bourne shell, if you're in a terminal, it's your shell. And the thing, it reads in commands and does what you say. And they separate this from the BDOS and the BIOS because what happens is, since you only need this to type in commands, and once you type in a command like, I want to run a program, that program, as I said, gets loaded into the TPA, and once it starts running, it can reuse the memory that the CCP is using. Your program can use everything up to here. When your program's done, it's going to branch up inside here, and it's going to reload the CCP backend down here so that it can call it again and run it, okay? And there's two different ways for your program to terminate to let the operating system know whether you've blown this thing away and to tell it that it needs to reload it or not, okay? One way, it says, I'm done, and I left it there so it can immediately pop right back in and give you a new prompt. But if you hogged all the memory when your program's running, which is very common if you only have 20K, every byte counts, this thing would have been blown away, and you return back, and you say, you better reload the CCP. And that takes a little longer because it has to reread this off the disk. Okay, so you'd like it to go fast if you can. Now, that's why this is on its own in here. Now, the BDOS is the thing. It's really a library in many ways. It's just a big old library that has a whole bunch of functions in it that provide services to your transient programs, okay, and the CCP as well. In other words, this is the BDOS is the thing that has a bunch of routines in there that say, I want to open up a file with a given name. The BIOS knows how to read and write sectors of the disk, blocks of the SD card. But it doesn't know anything about directories and data files or anything like that. So what happens is you're building up this like increasingly abstract construct of the file system that sits on top of the SD card, okay? And the job of the BDOS is to implement the file system, you know, on top of just a bunch of blocks on this disk that we're presenting to it, okay? So what we're going to see in this manual, if you scroll down in here, are instructions on how to call functions inside the BDOS. And then what you'll see is they're numbered. There's 37 total functions from 0 to 36. 0 means just obliterate everything and reload everything. This is essentially what you would do if you overwrite the CCP and stuff like that. This is, I need to reload everything. Then you have console input, console output. So what we're going to see is you're going to go through the BDOS, weasel your way through there, and end up calling the SIO, receive character routine. This is going to be our SIO transmit character routine. We don't have a reader and a punch device, so we'll just simply return an error or end of file or something like that to let them know there's no data to be dealt with here. And if it says punch something, we'll just throw it away and go on our merry way. All right? Listing is printing to the printer. And then you get some other fancy I/O operations that the BDOS provides, that you get for free. That's why you load an operating system. You want more than just crude, basic file, or rather, one byte at a time console I/O. You'd like to be able to have input editing. What happens when you hit the backspace key? Stuff like that. I don't want to write all that code myself. The BDOS has routines in there the deal with all that. And these functions will talk about that when you say, I want to look up what does function 2 do? What does function 1 do? What happens if I hit Control C? How does that, affect things? All right. So that's what is described in here. You don't have to worry about it in the BIOS code. The operating system, the BDOS, does all that for you. Opening and closing files and things like that. All right. And what you would expect an operating system to do. So let's take a look at one of these functions. It talks about various data structures and how files work and things like that. Here's your console input routine. Now this is from the perspective of a program running in that TPA. The idea is that if you write a program that runs on CPM and you behave yourself and only use these functions and you go through the BDOS to do all your work, then your program will run on any version, on any system, I should say, that's running CPM, in our case 2.0 or 2.2 or whatever you wrote it for, okay? We're shooting for 2.2 here. So if I don't just reach over and start dorking around with the SIO chip and instead go through the formal process here of reading a character. I put 1 into the C register, and if you read this documentation, it'll say put 1 into the C register and then do a subroutine call to address 5, and when it returns, you'll get the ASCII character from the console device, however that may work. It'll indirectly go through the BDOS and call into the BIOS, and it'll call the SIO routines that we've already written to get that character. And the reason you want to go through the BDOS to do all this is because of what it says down here. It says, look, if you got carriage return and things like that, they're going to be echoed to the console. Tab characters and so on will be expanded. So if I hit a tab, it'll move the cursor over the right way, as you would expect. If I hit Control S or whatever, the printer echo, we'll talk about printer echo some other time, and things like that. It's sometimes referred to as cooking the input here. It's doing some of the processing that a user would expect to see from certain keys that you may not want to have to implement on your own in every single program. All right. So we're starting to see very simple features of the operating system that are provided and standardized. So we don't have to dork around with them in our programs, nor do we have to provide them in the BIOS. And that is the entire point of having an operating system. All right. So let's close this and move on our merry way. We don't need to look at these other higher level programs till later. We were just looking at the interface guide. So you've got the 2.0 alteration guide and the 2.2 alteration guide. These are in 2 different websites, and I've spot checked these 2. These look exactly the same to me. But we are going to run 2.2, so let's read the 2.2 manual in case like one number somewhere is different in some way. Let's look at this document here. This is the alteration guide. And all right, now the thing you need to understand about this part of this project is that CPM was originally designed to be delivered to the consumer as a binary file. Therefore, they have a really special set of routines that you use to edit the operating system and configure it. Now, if you have the source code, you don't need to do any of this stuff at all. All right, so we're going to just ignore it completely. If you're a diehard, go ahead and read all this fun stuff, and you can do it in the binary files and all that fun stuff, and it certainly give you the full experience, but it's completely unnecessary, and it's much easier if you have the source code to just assemble it and to configure the system. And by that, what I'm talking about is the fact that the Z80, the 8080, this entire family of processors, the because they don't have virtual memory or what we call relative addressing modes for all the instructions, it turns out that if you assemble a program with like an org statement in there that says, I'm going to run starting at address, 1000 in hex, the assembler is going to put in your code all these references to, labels and data save areas and stuff like that. It's going to put the absolute addresses of all those things welded right in your code. And we'll see that in a little bit when we look at the BIOS and stuff like that. And what happens is if you don't want it to run there, which is what happens if you change the amount of memory, right? It could run at 20K. It could run at 50K, right? It could run at 64K. Well, if you need to move around the operating system, the CCP and the BDOS, someone has to go back and tweak all those address references. So they give you this special program that does all that for you so that the super secret, high and mighty, precious source code doesn't have to be given out to anybody. Okay? So you're jumping through massive hoops to reassemble a program without the source code is essentially what you're doing when you're playing these games here. All right? We don't have to do that. We got source code. We can just reassemble it for real and skip all this malarkey here, okay? Then this get sys put sys jazz is what you need to do if you have your disk and you have no operating system at all. How do you get data off the disk and then back on it so that you can replace the data that represents CPM and your BIOS? How do you get your BIOS on the floppy disk or on your hard drive or whatever, okay? So they go over the process of writing what we're using as DD, okay? We have other systems that can access an SD card and read the SD card and write onto the SD card. I've been talking about that for weeks. We don't need to write our own get sys and put sys programs because that's what DD does for us, all right? So we're already now up to page 12. We can start talking about disk get organization. This is going to be a description of how CPM thinks of the disk. This is super important to us, all right? So let's dive in here because we don't need to worry about any of this stuff there. We'll take a quick eyeball on the introduction just in case we stumble into something interesting there, but our job starts here in section 5, okay? The introduction says that it explains that this whole manual is going to give you the entire source code of a BIOS for this machine right here. All right, the MDS 800. And it says that when it's delivered to the customer, they're going to give it to you as on an IBM 3741 format compatible disk, a floppy disk. In other words, a single-sided, single-density 8-inch floppy with 77 tracks and 26 sectors per track, and the sectors are numbered from 1 to 26 for some unknown reason, and the tracks are labeled from 0 to 76, just to make sure that inconsistency bothers me personally. That's my theory. I think that they were after me personally when they did that. Obviously, just kidding. Now they go on to say it's configured for single density, just like I explained, but you can field alter the system so that it can run on different kinds of disks with different geometries. And that's what we're going to do, okay? And it's going to be a little more comfortable for us since we have the source code to reassemble it so we don't have to play around with all the sysgen stuff. So what does it say? In order to achieve device independence, it's separated into these distinct parts. The TPA is not mentioned here because the operating system does not include the TPA. It includes these 3 parts that put stuff into the TPA to run them, okay? So what we're going to do is we write the BIOS, and even though we have the source code to these things, we're not actually going to tweak this, other than some errors that are in the distribution file that we'll look at in a minute. We have the source code. All we're going to do with this is just simply reassemble it at different addresses. So we can change the origin. So we can run it at 64K, 50K, wherever we want to put it. All right? It's the only reason we care about the source code. Otherwise, I don't even look at the thing. Okay? We also say that only the BIOS is dependent on the particular hardware. Again, reiterating the fact that the CPM can run on any machine with an 8080 or Z80, provided that someone somewhere writes a BIOS that provides a certain set of functions like read a disk sector, write a disk sector, read from the console, and so on, which we've already done all those parts, okay? And that's what you need to really know in order to understand how this thing all works. And that's why it's super duper portable. This is actually pretty cool, and they get credit for being one of the first groups to kind of create this idea that there'd be a basic I/O system independent of the rest of the operating system so that it could be run on many different machines. And CPM ran on a very wide variety of different pieces of hardware with different CPUs and everything. The exact same binary files for the BDOS and the CP always worked because the only thing that needs to change is the BIOS. And all the transient programs work fine as long as they make calls into the BDOS the way the interface guy says to do them. All right. Okay, so now we get into all the how do you regenerate, system generate, and this is exactly what I was just saying. Depending on the amount of memory, you need to make these adjustments and change all the addresses inside the code based on these distances, and we can skip all this because we're going to just build it to run at the size of memory that we have and forego all that. So what we need to do is what? Go down to section 5, which is on or around page 12. In here, because it's going to start with table of contents on different page numbers, and it gives you some what it's here in section 4. Oh, this is the get sys put sys stuff up here, right? And we don't care about that because we already have a way to deal with that. We get on a diskette organization. Here's where our job really begins, because our SD card needs to be visible, needs to be presented in the form of a disk that the CPM can understand. Okay, now this is going to describe first how the machine boots. The way they expect the system to start, it says right here, program in the very first sector on the very first track is called boot. This thing has the responsibility of copying in all the other sectors into the memory, starting at the location of something plus B. Right? This is going to be where our CPM needs to sit in our RAM. And that has to do with this load base thing that we saw in the last video. Okay? And then it talks about if your controller does this, you can do this, that, you can do that, blah, 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 blah. What ours does, from the perspective of this documentation, our boot firmware is going to read in 16K. There's only reads in one single sector, 128 bytes in CPM speak, right? Because one sector in CPM is 128 bytes. I'm not interested in 128 bytes. So, and we own the whole thing. We can do anything we want. So I made my firmware read 16K off the SD card, and because each block is a half a K on an SD card, it's going to read in 32 blocks, and it's going to put it into memory starting at C000 all the way up through FFFF. Okay, that's how our firmware is going to load in this system. What this talks about here is a simpler version of that, where they read in one single sector, and a tiny program in the first sector has enough code in it to read in all the other sectors, which would be, in my scenario, the 16K. Okay, so it does a double leapfrog. I'm going to just do a single leapfrog. Why? Because we can. It's just a lot easier. So then what happens here? And they talk about the MDS 800. And it says, for example, that bootloader loads in the first sector into this address here. And then it's going to branch to that address. And then the code in there is going to do what's necessary to get the rest of the data read into the memory, okay? Ours is going to read in more, and it's going to put it in at C000, and then it's going to branch to C000. And when it gets there, we don't have to do any more reading from the SD card. We're just going to initialize CPM and make the thing go. Okay? So what they do is they give you a diagram here that shows each sector on each track of the 8-inch floppy disk in its standard distribution, what each one's used for. And we're going to see this come up in our code. The CCP has a very specific number of bytes in it, and it's designed specifically to fit in to exactly this, whatever number of sectors this is, 2 through 17, which should be 15 sectors of the floppy disk. Here's the first sector on the first track, track 0, sector 1, is they're using it for the cold start loader, which we don't have, okay? But we're going to still put something up here because it expects there to be something up there. So the CCP is on there, followed by the BDOS immediately contiguously after the CCP, and then you got the BIOS down here. So our job is to take the CPM stuff, which is the CCP and the BDOS, and just glue our code for the BIOS right on it, right after where the BDOS ends. And there's a very specific set of addresses. There's a branch table that our BIOS must start with a very specific set of addressed jumps and stuff like that, because the BDOS knows that, or expects that your BIOS will have this very specific set of jump instructions at the very beginning. After that, you're free to do anything you want in your BIOS, okay? Now, with all this in mind, let's look and see how we actually build and run this. So if you go into this retro directory, I give you here's the whole thing. Type make and then do this. Okay, right now that's all we really need to do. But let's look at the code and see what happens there. All right, so I'm in where am I? I'm not even logged in here. So let's log into the Pi and let's see what's going on. Here's our CPM repo. All right, so we're going to go into the CPM22 directory here. And what we'll see in this directory are these files here. Let's look at the make file. Like I said, you got to download these pieces and then unzip them to get the parts out that we want. All right, then there's 2 files here. One we'll deal with later after we get our system running. But the first file we need to grab is the actual CPM operating system, which is buried in this thing, I think, here. So what does this thing do? It needs to create a CPM22.Z80. This is the source code of the operating system right here. This is going to be a directory that's going to include, that's going to contain a bunch of files that we need to put on our CPM disk. Those are going to be the files that are like the assembler and the stat command and the DDT debugger or the editor and stuff like that. All our programs that need to end up on our SD card. Okay, then you'll see there's going to be a way to deal with all that in here too. But we're going to prime it with these standard distribution files here, okay? So what is this make file really going to do? What this rule here is it says, in order to create this CPM22.Z80, you have to first have this zip file. Once you have that zip file, however that might be, and it's down here, it'll simply unzip that file and extract this thing out of it, okay? Now I do a touchdown here because unzip will backdate the file. This is just housekeeping if you know how the timestamps and stuff work for make and things like that. This just makes sure that this file has the current time on it once you take it out of the zip file. So where does the zip file come from? Well, it comes from this rule down here. It says I can create the zip file out of thin air. It has no dependencies. In other words, if make does not already see this file in the current directory, do this, and it will miraculously create it out of nothing by downloading it from this website here, okay? So when I type make, it's going to say I need to create these 2 things. And the first thing it's going to do is say I need this, and if it doesn't have it, it'll get it. Then it'll unzip it like I just said. Then it'll say I need to have this thing called a file system. What's that? Well, that's a thing that's dependent on another zip file, and it's created using these rules down here, okay? And if I want to get rid of the mess that I create, I can type make clean, and it'll delete all the stuff. So the state I'm in right now is when I clean up, I don't delete these zip files, okay? Because I don't want to have to re-download them over and over and over again. Once you type make the first time, it'll copy these, it'll download these files from this website here, okay? And then when it is done with that, I wonder if this one's got a bug in it. It doesn't say HTTP in there. I think that's a mistake in my make file. I don't know how smart wget is. It might need to have this in front of it. Well, I'll test that after we're done here and come back and fix it later if it is a problem. And these obviously came from somewhere, so this might be right, but I'm just inconsistent, and that's bothering me here. Anyhow, once these zip files are here, if you type make, you'll see it do, here's the unzip, and it grabs this file out of it, and then it wants to create this file system. And if you type, well, these are the files that you need to put on your disk. If you're actually going to run CPM, these are the standard files. Here's your editor, your assembler, this dump program. Here's their sample BIOS, if you want to look at it, and your, a README file and DDT and stuff like that. This thing here is part of the sysgen process. I don't have the sysgen files in here simply because we don't need them. All right. I don't know why I have this in here, but whatever. It's in there because it's in the zip file. We don't need it. Okay. So once you have done this, the point is there's your source code. Okay. So if we open this up and look at it, we can see this is the source code of CPM. It's got various things going on in here. And you can see the very first line of code won't work with Z80 ASM because these symbols here, these labels, need to have colons after them. All right. And I don't want to hard code the memory size here either. So I wrote a little editor script that's going to go in this file and change all these things that are not compatible with the assembler that I'm using. It's also going to change some stuff down here. If we sift through here, there's some mistakes in whoever created this file. I have no idea why they don't fix them. People talk about it. Why doesn't anybody fix it? I don't know. I could create some conspiracy theories, but it turns out that sometimes when they put HL, I want to put B and store it in memory at the address in HL. Here's one right here that's wrong. That is the 8080 style, right? This M, when you use a register called M in 8080 assembler, it means the same thing in Z80 when you put HL in parentheses. So somebody went through and adjusted all this code so that it is written in Z80 assembler, but they screwed up a few instructions like these, okay? If we go to assemble this, it won't work. It won't work because not all the labels can have the colon after them. In some of these times, they missed some of these references. You have to change M to HL in parentheses, okay? Since I want you to be able to download your own and make it yourself, we have to now edit this. So what I did here, that gets you the distribution for these are the naked raw distribution files right there. If we now go into the retro directory, make sure it's clean, and you start with this. This is just some more test files and stuff that I'm working on that I need to upload when the time comes here. What happens here is we look at this make file. There's a lot of crud going on in here. You recognize this. This is the command that I use to substitute the git repo and the date and all that stuff into the source code of the assembly language program, right? And then so that later on we can assemble it and we can put in information about the git repo and stuff like that. And down here we're going to do the same thing, and there's a typo that I can fix right now. So the well, this comment we'll discuss later. What I'm going to do here is I'm going to say, look, I need something called CPM22.asm. And what it's going to be literally is it's going to be a copy of this file that I downloaded. But first thing I'm going to do is I'm going to expand all the tabs because otherwise it doesn't line up right when you run it through the Z80 ASM. And I've got another super nasty sed command in here. I'll leave it as a task to the viewer, and I will observe that this here comments out the memory macro that I said we don't want in there. We don't want it hard-coded in there. This one here changes the M to the HL in those cases when it is wrong. All right. This one over here is going to create, I don't know what the heck that thing does. I don't know why these are jump instructions or something. This probably has to do with the colons that are missing in the labels, as does this one down here. Okay? So this is going to fix the errors and incompatibilities with the source we got and convert it into what we want. Okay? Then once we got what we want, this will assemble it. It'll convert this into an executable file when we compile our own BIOS and stuff like that. Okay, so you can poke around in here and look at it and figure it out based on what I told you before, if you even care. So let's look now at what we actually do assemble when the make file here, right? We don't actually assemble the CPM file directly. You're going to see we include it into this one. So this will look fairly familiar. We're going to include IOASM and memory ASM. We're going to create our stack, and we're going to org to load base. So this is going to start out the exact same way our little hello program worked, okay? This is going to go in our partition number 1 on our SD card. And it's going to start at C000. So when the firmware loads this out of partition 1, it's going to load in, this is the 16K. It comes from this file right here. And it's going to put it into memory, and then it's going to branch to load base, and it'll execute this instruction right here. What does this do? This is the thing that's in that first sector, so to speak. It's the thing that comes before the CCP that's on the disk, filling up that space. So all it's going to do is jump over this, the entire, this is where the CPM, all the CCP and the BDOS and all that stuff is included into this file, all right? So what we're going to do is we're going to jump from the beginning over the entire operating system and some other junk that I'll talk about in a minute, and land way down here at this label over here. So we're going to jump from the beginning of the load base all the way up to the into near the beginning of our BIOS, right? Now, as we'll see next time, that it's the job of the BIOS to take care of getting the system ready to start up the CCP. And they give you very specific instructions on what to do, none of which I've done yet. I just want to be able to assemble the darn thing and get all the pieces into the SD card and boot it, okay? So what I'm going to do here is make sure that I can assemble the thing that I've downloaded and run through SED and fixed all the labels and everything. Then I'm going to actually put this thing in place here. That is as I said earlier, the BIOS must have these specific jump instructions at the beginning of it. This is the entry point to all the subroutines that we have to provide in our BIOS now, okay? Now, because of the memory that it, and it said, hey, here's what the disk must look like, and the CCP must use exactly this many sectors of this many bytes. The BDOS must use exactly this many sectors of this many bytes, and the BIOS must come immediately after all that stuff. Okay, that's what this is checking here. Look what's going on. The boot flash code loads a big blob into memory at load base. It then enters in there and it jumps over this reserved area for the, arguably, the other half of the bootloader that we don't need. Okay. If I don't use the right number of bytes, and the CPM, the CCP, and the BDOS and stuff don't start at the right place, then what will happen is my code down here won't be at the right place. Okay? So one of the things I do right here is I check to make real sure that when I did the sed command on this file, I didn't break it and create a situation where there's too many bytes in there or too few. All right. So what I'm doing here is I'm saying, look, if the CPM base, which is a label that's defined inside here, which is the beginning of the CCP, plus exactly 1600, which you look up in the table over here. Okay. If you count all this out in hex, if this thingy here plus 1600 does not equal that, okay, then we didn't do it right. Okay, so this checks that. That's all I'm saying here. So read in this file, make sure it's exactly the size it's supposed to be, otherwise gripe, okay? And this is just a convention I invented. If this is not equal and it tries to assemble this, it'll give you an error of some type that is going to be hopefully self-explanatory. So that makes sure that these go where they're supposed to go. They're right now not yet used. They will be next time. We'll start playing with that. And then after that is the code that will wake up. It's going to set up its stack. As you can see in here, what we're going to do is reinitialize the whole retro board. We don't care that the firmware did this already. It might have done it and set a different baud rate, or maybe the firmware was set up to use a different serial port or whatever. We don't care. We're going to start from scratch and redo everything. We have our own copy, we have our own cache and our own everything else here, okay? So we're going to divorce ourselves from the boot flash. And we're going to reinitialize our copy of the cache and make sure it's where we want it to be. We're in bank 0, make sure the SD card's idle and stuff like that. It already is, but we need to initialize our cache to make that match the output port. So we're going to just redo it here anyway, okay? We're going to do the usual thing and reset the stack, and this one's going to set it to 0 and let it wrap all the way up and around. And so our stack is at the high memory. We're going to call a function called init console, which we've seen 100 times. Then we're going to look at we're going to print a message here. We're going to put the address of this into HL, call put s. We've seen that 100 times. Then we're going to jump to something called halt loop, which we'll see in a second here, right? So this is all stubbed in. These are the subroutines that we need to write. Those are the things that are jumped into from up here. We can't put the code up here because the BDOS mandates that this jump and this jump and this jump are in this exact order and nothing else is between these. It's an absolute rule for CPM. So CPM is going to call whatever one of these it wants, and they must be here. So what we're going to do is just jump somewhere else to give us room, all right? And right now, our entire BIOS, all of our functions, if any of them get called, we'll just go down here and seize up the thing. Okay? If we can get this thing to just say hello and stop, it's a miracle, right? So here's our init console. We've seen it 100 times. We're going to just redo what we always do. You've seen this 100 times. Include libraries that we care about. And I've got these stubbed in because that's where we're heading. Very next thing we need to be able to do is get these all the BIOS routines in here. Here's our output cache, all ready to go. Okay, so if we assemble this thing up, you see the editor run and adjust all of the labels and stuff. If we type another ls, you'll see this file miraculously appeared because that was copied out of the other one and the said command applied to it. Then here's our ASM, included it inside of itself, and it built it and created a binary file. We didn't get any errors, so we're very lucky. If we look at the listing file, we've seen these before. We see it starts out with our BIOS, and then down here it includes the I/O thing. We've seen that 100 times. Here's the memory file. We've seen that a bunch of times. It's going to be a little bit more obvious this time because here's where I define this memory size. Okay, I put it in here so that I'm kind of setting it for CPM because I don't want to edit the CPM. I want this in my own files, so I'm configuring CPM. This basically, one line right here, is the entire job of that sysgen move CPM stuff. All right? By just defining this myself, we alleviate ourselves from having to do all that other rigmarole. All right? Here's where CPM base is defined, and this is because of how CPM wants it to be defined. I don't know why you don't just define the memory where CPM starts. You kind of define it where it sort of ends, and then you back off 7K, whatever. This is just how it wants to be told where it starts. Here's our load base. We've seen that a couple of times. Stack is 0. This is the end of the memory file, so this is back into our retro.asm file, right? So look what happens here. This defines space, defines storage. I'm just padding memory out to D400. All right, it's a lot more than one sector, but this is necessary because our firmware loader doesn't care where CPM actually loads. The firmware loader is going to put whatever it reads into load base, which is this address here. This code here will pad memory out to where CPM base is based on how it was defined up here, okay? The idea is if I decide to change the memory to make more room for my BIOS, the CCP and stuff have to load at a lower address. This will creep down, 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 okay, if I need more room for my BIOS. If it ever gets all the way down to C000, we got a problem, okay? But if that happens, we'll just rewrite the firmware, the flash code, okay? But as long as it stays above C000, we're fine. And we just have to pad it out here in order to make sure that this number here matches the address that is in the CPM base equate. And this is how you do that, okay? Now down here is where we actually read in this enormous CPM thing, and you can see now the memory's commented out there, and all these have their colons and everything else, and it wouldn't assemble if I didn't have the HL jazz and stuff done right. Now I'm going to go to the far end of the file because CPM is pretty big, and I'm going to go backwards down here, all right? So now down here, there's your hex dump, and your put S and your CTC driver and probably the serial driver there. And you can come back here. There's the and here's our init console logic and the halt loop, and you recognize all these pieces, okay? So what you're looking at here is me gluing together the CCP and the BIOS, or the BDOS, I should say, along with our BIOS right here. And we're doing it by simply taking all these source code files and gluing them together and just assembling the whole wad at once. We're accomplishing the same thing as move CPM plus the regen, the sysgen, and all this other stuff, and the get sys, put sys, and all that jazz, all in one big file here. And then we can use the DD command to write it out to our SD card. All right. If we look at the README file that you can find on the GitHub repo. This is our put sys, okay? So let me put the SD card in my Raspberry Pi, make sure the partitions are right, put this into the partition number 1, and boot it up and see what happens. All right, so I've taken the SD card and plugged it in to my Pi. And if you do this, you can see there's the whole SD card, and there's partition number 1, like we've seen before, right? Now, if I do this command here, and we've seen this with the hello, all right? It's really the same thing. It's just a much bigger hello program. We're going to take the binary file for the whole retro thing, copy it into the first partition, and make sure that it writes it, and hopefully in integral blocks of 512. You can see the retro binary is not terribly big. That's all of CPM plus a teeny tiny BIOS, but luckily it's less than 16K. That's the critical thing. If this is over 16K, it ain't gonna fit, right? Well, that's when we have to change our flash logic to read more data in if we want that, okay? So here we're going to do this. We're going to write that thing onto the card. You might do a sync if you really want to. Pull out the card, put it back into the Z80 board, and hit reset. So here's my Minicom. I put the SD card back in the retro board, and the retro board still has the flash programmed for the hello program app. In other words, it's going to read the first partition, the 16K, and branch to it. And voila, it worked. This is our BIOS starting to boot, followed by it stopping. Okay. Quick recap. Look what's going on here. Here's the flash loader from the other day that I still have loaded from this is when I recorded that hello video, the last one I did. And it prints out I'm booting from partition 1. It dumps out the partition table. And we walked through the logic really briefly in the last video on how this works. This is a variation of the other read routines that we looked at more closely, and with a little more debugging information on here. It says partition 1 starts at this address, and it says the number of blocks in the partition partition is here, and it gets all that from here. This is the entry here. You can sort of see the 00040000, the LBA, or the logic block size here, right? And you can see the 00000800, which is the LBA where it starts, okay? So I just extract all this out as debug information so that I can see that my program read this partition table correctly. And if it ever crashes down here, and this one's not, the right number or something, at least, I'd have some clue what's going on. And then it reminds me also, by the way, I'm loading hex 20, which is 32, half K blocks into this range of byte addresses. Again, in case I forget, wow, this thing works someday. All these dots are printed out in the loop. When it reads each block one at a time, it prints these dots out. So there'd be 32 of these. Again, if it kind of prints some and then hung up or something, I would know that my code was broken or something like that. A little debugging aid. Plus, something to keep me occupied, since it does take, half a second or so to read all this stuff. Then it branches up, and we clearly see the output from what our program's supposed to do. It's dirty because I edited some of the files and corrected a typo in the doc and stuff like that, all right? But this is the right time. This works. Okay. So from here on in, it's add one feature at a time and test it. Add one feature at a time and test it. The first thing we really want to do is get the console I/O working, because that's what the CCP really uses. And when we do that, we can stub in the disk routines and basically fool the operating system into thinking that, yes, it has a disk and all is well, but there are no files on it. Don't worry about it. Okay, so that's the next couple of leaps we're going to make. Hopefully you've got enough to get started on poking around here. Have a look-see at the alteration guide, read through it, and familiarize yourself with at least the parts we talked about so far. Start looking at what all those the dozen or so BIOS jump vectors do, okay? Like how to read the console and all that other fun stuff. So, this has been another long one. Woo! Anyway, thanks for watching. I'll see you next time.